Hello again to another Agakala React, and today we will be watching Everyone is Wrong About Asteroid Mining from the Space Race. Another channel that I'm starting to watch more and more often, so let's just jump in and see.
We all want to live in a world of abundance, but in order to find that dream, we will need to go far beyond our own world. Mining in space, the final frontier of resource extraction. Because everything that we could ever need, every rock, metal, and gas to support a boundless human civilization from now until the day that the sun explodes, it's all out there in our own planetary neighborhood. So close, yet so far. This is the big problem with space mining. In theory, it's a simple idea. We go to a nearby asteroid that's full of valuable metal. We break it open, extract the good stuff, bring it home, and boom, unlimited wealth and prosperity. Neil deGrasse Tyson once said that the first trillionaire will be the person who mines asteroids for resources. But there's more to this than just getting rich. Taking resource extraction.
I wonder when he did say that, because isn't Musk a trillionaire now? Isn't it?
Action into space could take pressure off of the environment on our own planet. It could even be the key to us reaching new planets or even new solar systems. But it's not just easy money out there among the stars. This is a logistical nightmare, to say the least.
True.
It's going to be spectacularly difficult, preposterously expensive, and more than a little dangerous. The first place that we are going to want to look when scouting for our mining location in space will be asteroids. They are the closest and most worthwhile resources in our solar system. The surface of the moon or Mars is just not going to be dense enough with the good stuff to be worthwhile. Planets are actually the worst places in the solar system to mine because all of the best resources are buried too deep under the surface. The reason we like asteroids is because they are essentially leftover raw materials from billions of years ago when the solar system was formed. All of the metal, rock, dust, and gas that never got the chance to become a planet instead became an asteroid. That means that asteroids are made up of the same stuff as planets, but in a much more concentrated and accessible format. When a planet forms, everything gets very hot and molten, which means that the heavy metals will sink down into the structure, and the heaviest elements will gather in the middle and form the core. That concentrated mass creates a gravity well, which then pulls in more stuff and eventually makes a planet. Many asteroids never went through that melting and settling process, so you can still find massive chunks of heavy metals just floating around out there. And these are the most interesting in terms of mining them for resources.
Okay, so far, yeah, it's probably something that we're gonna, like, I know there's probably people that are already thinking how to do it. Although this technology is probably not there yet, but there are obviously a lot of science fiction talks about it. And yeah, so it's not something we can't say that we're not going to do, because we are going to have to do. Because if we're gonna need, for progress, we're gonna need materials, the rare earth materials that they probably out there in space, and things to progress the science and technology and all that. So it's gonna have to happen at some stage in our future, not history, but in our future. And like I said, I often say in cases of this, is it gonna happen during my lifetime? Probably not, but it is going to happen at some stage in the future. It's not that we're gonna be staying just on Earth. They're already planning to go to Mars, to go to things, so why not go further into the asteroid belt and just start mining stuff there, because that's what's gonna have to happen, isn't it?
M-type or metallic asteroids are typically composed of 80% iron and a 20% mixture of nickel, iridium, palladium, platinum, gold, magnesium, and other precious metals that are obscure and difficult to pronounce, but still very important. There are single asteroids out there that contain more nickel than all of the available nickel in the Earth's crust put together. Even more interesting than that, is the presence of these rare earth metals like platinum, palladium, and rhodium. These elements are the reason that catalytic converters from gasoline-powered vehicles have become such a hot commodity in recent years, and why yours may have been sawn off in the middle of the night and stolen by a bunch of gangsters. Rare earth metals aren't exactly rare on Earth so much as they are just very difficult to find. Platinum group metals don't concentrate into large veins the way the gold ones do. They're just scattered all over the place in small amounts, but this isn't the case on a metallic asteroid. Again, just one space rock a few hundred meters across might yield more platinum than has ever been produced on Earth, or will ever be produced on Earth. And wouldn't it be amazing if we could just source all of the exotic metals and things that we would need from asteroids? If we could just stop mining the Earth and mine outer space instead. This is 16 Psyche, possibly the most valuable asteroid in the solar system, and likely also the largest. This one lives in the asteroid belt between Mars and Jupiter. It's widely believed that Psyche is actually the formed core of a dead planet that somehow lost its outer layers. So remember how we said that all of the metals get pulled into a planet's molten core as the planet forms? Well, that means Psyche is a concentrated mass of heavy metal. The estimated value of 16 Psyche is something like $10,000 quadrillion, which is just an unfathomable.
Quadrillion? Is that past trillion? Yeah, 1 second. Millie's here. Millie's here. Yeah, quadrillion. That's a number that you don't hear often. Yes, Millie. I think it's kind of when you hear quadrillion, you just hear that in regards of space, isn't it? Quadrillion miles. How much is quadrillion? 1 second. I don't even know how to spell it. Quadrillion. Is it Q or is it K? Quadrillion. So quadrillion is a large number representing 1 followed by 15 zeros. In the US and Canada, this is the standard definition, while in Britain, a quadrillion is defined as 1 followed by 24 zeros. Oh, interesting. So, names of large numbers we have here. Here, show you. So we have million, billion, trillion, quadrillion after trillion, then quintillion, sextillion, septillion. Wow, okay. Millie! Why are you meowing so much? Did I just turn off my thing? I did turn off the video that I was watching. That's not good. It's very bad, actually. Let me go back. Yes, Millie. I know, you're hungry.
You won't.
Yes, there's an ad here as well. So guys, what I'm gonna do...
He's making you lunch.
What I'm gonna do is pause here for a second because Amelia is not going to stop meowing now because honestly I forgot to feed her and it's a bit after her time of feeding and she needs her medicine as well. So I'm just gonna go through those ads, they're not that long, and then I'm gonna come back. Thank you. I'm back. Amelia got medicated and fed and we can keep watching.
And likely also the largest. This one lives in the asteroid belt between Mars and Jupiter. It's widely believed that Psyche is actually the formed core of a dead planet that somehow lost its outer layers. So remember how we...
Just a reminder, I did, when I started looking how big is quadrillion, I did search on the same page, on the same tab that I was watching in, so I had to go back. There you go.
We said that all of the metals get pulled into a planet's molten core as the planet forms. Well, that means Psyche is a concentrated mass of heavy metal. The estimated value of 16 Psyche is something like $10,000 quadrillion, which is just an unfathomable value, and that's...
Yeah, because I didn't even click the fact that he said 10,000 quadrillion. And I can't even fathom how much is trillion, and the quadrillion is after that, and he says it's 10,000 of that. So it's like,
It's the dragon that would-be space miners are chasing. One big score that unlocks more wealth than the entire global economy put together. That raises some interesting legal questions.
yeah,
Can you own an asteroid?
exactly.
Well, no, but there is actually something called the United States Space Act that was written in 2015, and it
Yeah, but it's
says
only United
that
States.
American companies are allowed to own the materials that they mine from bodies in space. So it's a finders keepers,
American
first come, first
companies,
serve kind of deal, meaning that the race is on and the stakes are high. But before we even get into the logistics of mining on an asteroid, which are insane, there's one fundamental problem that can bring the whole operation into question. Once we unlock an unlimited supply of a resource like nickel, then it stops being rare and by extension, stops being valuable.
True.
Of course, it's more difficult than that, because while the supply would be abundant, the access to it would still be restricted because it requires flying through space to collect and bring back. Add to that the limitations of carrying capacity of a spaceship. So far, the closest thing that we have to a functional interplanetary cargo vehicle is the SpaceX Starship, with an estimated cargo capacity of 100 metric tons.
That's not that much.
The annual nickel production on Earth in the year 2020 was 2.5 million metric tons, which would equal 25,000 Starship loads of pure nickel per year for asteroid mining to even match Earth mining, which would be on average 70 Starship launches per day, every day, on a round trip that would probably take 2 or 3 years to complete.
Yeah, this is where we have to get into building like space stations that they are not just for. This is probably how it's gonna be. The space station is gonna be built for refining all those material and stuff, so then it can be actually used on Earth, or even like with, I don't know, shrimp. What is it? Fishing? Is it? I don't know. Is it shrimp fished? So basically, you fish it there and you processing it and freezing it or cooking it straight away on the boat. It's pretty much gonna have to be thinking about something like that, isn't it?
That's not exactly a scenario that we would call practical.
No.
It's a real head-scratcher of a problem. And even with a confirmed jackpot on our hands, reaching these asteroids will be incredibly difficult. Most of the metallic M-class asteroids orbit right in between Mars and Jupiter, at the center of the main belt. That's pretty far away from Earth, not on the cosmic scale, but on the human scale. That's a lot further than we typically venture. We are already pretty good at sending refrigerator-sized probes into deep space, and we can land a rover as big as a car on the planet Mars, but asteroids present a unique challenge. We know that we can land probes on asteroids. That's been accomplished already. The Japanese Space Agency began their Hayabusa or Peregrine Falcon mission in 2003 to explore near-Earth asteroids. Hayabusa 1 landed on the Itokawa asteroid in 2005. This is a fairly small object at less than 1 kilometer in diameter. The probe landed on the asteroid and collected samples in the form of tiny grains of material, which were returned to Earth aboard the spacecraft on June 13, 2010. Now, this wasn't the first probe to land on an asteroid, but it was the first to land, take samples, and then come back. The Hayabusa 2 launched in 2014 on a mission to the asteroid Ryugu. Again, the probe surveyed the rock, collected samples, and returned them to Earth. The payload from that mission arrived in December 2020. And then NASA got in on the action with OSIRIS-REx. This sample return mission, which launched in 2016 to the asteroid Bennu, which is not a metallic asteroid, it's the more common S-class or stony asteroid. The sample was returned to Earth in 2023, and in January 2025, the first research paper was released with analysis of the asteroid material. Both the Japanese and NASA asteroid missions have been focused exclusively on science and not identifying resources for space mining, but these close encounters have been incredibly valuable in helping us to understand the true nature of asteroids, and that's going to inform the approach that needs to be taken when it comes to mining them. The biggest change in our perception of asteroids is that we don't see them as giant rocks in space anymore. What we've learned is that most asteroids are actually more like loose piles of rock, dust, and metal that are held together by a weak force of gravity. Out there in deep space, far from the influence of any planets and their gravity well, objects with significant mass will draw in other objects via the force of gravity, kind of like a magnet, but it's a very weak pull. This leads to a slow process of asteroid formation that plays out over millions and billions of years. As the asteroid moves through space, it accumulates more loose rocks and dust, like the Roombas of the solar system. And as a result, there's not enough energy being pulled together to cause the melting and combining necessary to produce a solid rock. Anyway, if we've successfully visited asteroids before, can we just scale up these small probe experiments into full-blown resource extraction? Well, not really.
Not yet, anyway.
Let's go.
That's the problem, isn't it? Just the technology is not here yet, but eventually it will. And yeah, I was just talking there over not that long ago about what I had to say, and so far it's just the only thing that I have added. There's nothing new that I want to add to what we were just watched now. So I'll be back in a second. Okay, I'm back, and as usual, let's just jump back in and finish up.
The reason that it's pretty easy to get a probe to an asteroid and make contact is because the probe is super small and lightweight. NASA's OSIRIS-REx probe is just 2.5 meters high by 3 meters wide. It weighs just over 2,000 kilograms. Just try and imagine the scale of the spaceship that we would need to launch a mining industry on 16 Psyche. It would be humongous, and the weight of it would be unprecedented.
I think it would have to be built into space. That would be the easiest way, isn't it? So, yeah, another 200 years for doing that.
Rig would have to be assembled in orbit because it would be far too massive to reach escape velocity from the Earth's surface. So that's going to need an equally massive rocket engine to burn with enough force to get this ship up to the velocity it needs to reach the asteroid belt in a reasonable amount of time. Then, on the other end, that engine needs to burn again with the power to bring this whole thing to a stop. When we land a spaceship on Earth, we rely on the atmosphere to handle the majority of the deceleration energy. But asteroids don't have atmospheres to help with that. And they don't have gravity either, which is another problem. Psyche might have enough mass for microgravity, but it's believed to be just 1.5% the gravity of Earth. That's even significantly lower gravity than the Moon. And that's the biggest, most dense asteroid we know. All the others have even less gravitational force, which is to say they basically have none. So remember that climatic scene in Armageddon when Bruce Willis has to dramatically pull himself up out of the hole on the surface of the asteroid just in the nick of time to set off the explosion and save the world? Well, that would never be the case in real life. Bruce Willis would actually have the opposite problem of struggling to keep himself and his stuff from just floating away into space. And that's a really big problem for trying to mine an asteroid. The easiest way that we know how to mine rocks on Earth is to drill a long hole, put explosives in it, and then set off a huge explosion that breaks up the rock, and then we extract the rubble. But if we did that on an asteroid, all the rubble would just shoot straight out into space. Any rock that we break free from the mass of the asteroid will not be sticking around. So that's just logistical.
What about the simple just scraping thing? Because I'm guessing it's all kind of like material. So just scraping all the material from the top, layer by layer, and just using that too. Oh, okay.
Craziness to try and figure out. We need some kind of a combination rock crusher and vacuum machine thing. So here's the more practical approach. We capture the asteroid in a giant bag and melt it. In this strategy, we don't have to worry about landing on the asteroid at all. Our spacecraft would approach the target and match its orbit, then deploy a large plastic containment bag that would envelop the entire asteroid.
That is an interesting idea, for sure. But I don't think I ever seen anyone trying to do something like that in any of the science fiction that I read or watched. But it's a very good idea, actually. Although the plastic, I mean, there's such a strong plastics now that it would be possible to do the one that wouldn't melt from the heat they'd have to do. Okay. And yeah, I'm gonna see you again because it's another ad. Yay! Cool, huh? Yeah, I see it. Alright, I'm back, and again, after a long I don't know what I'm talking about now. I'm just getting really tired now. So, we have only, what, 2 minutes left?
Once we have the asteroid in the bag, now we need to heat it up. That can be done by either using a giant reflector to concentrate sunlight, or by blasting it with a laser. Regardless of the method, the goal here is to vaporize the material in the bag until it becomes a big cloud of atoms. Now we sort those atoms, separating the valuable resources from the plain rock and dust. Then, only the most important material in a pure form is returned to the Earth. Compared with a traditional digging method, or trying to pull an entire asteroid back to Earth orbit, the contain and vaporize method is the most likely to succeed in a way that's both effective and affordable. We have to figure out not just mining in space, but refining as well to make sure that only the most valuable resources return to Earth for sale. It's not that Neil deGrasse Tyson was necessarily wrong when he said that asteroid mining was the path to trillion-dollar fortunes, but he didn't really specify that this only works as a long game. It's not easy money. The upfront cost will be enormous. The cost for NASA to return just 1 kilogram of loose material from the surface of asteroid Bennu was around $1 billion. By comparison, 1 kilogram of platinum metal is worth about $32,000. That math is pretty far from making sense at this point. Consider this, there are 20 million tons of gold at the bottom of the ocean. No one has been interested in going down there to get it, and even mining the ocean floor would be a lot easier than mining an asteroid. So to get the real value of asteroid mining, we need to take money out of the equation. This isn't making money, it's about saving the world. Mining on Earth sucks. It's bad for the environment, it's bad for the people involved, and it's not a sustainable practice that we can just continue on for thousands of years into the future. Eventually, we run out. And asteroid mining is the answer, but it's not an easy one, and it's only going to work when done for the right reasons. Not necessarily for wealth, but for the good of the Earth and the people living on it.
I think the other reason for it gonna be as well progress of the science and technology. I think that's a reason for it, good reason for it too. So yeah, do I have anything else to add? Unfortunately not, because I was kind of talking through. I think I kind of gave all my points out, and I just don't want to repeat myself too much. So thank you very much for watching, and I see you tomorrow. Bye!